find out. I hope you have numbers from the last workshop so that I can write them down again. And today we have to finish with other modules. But all these modules are very time consuming to run. And that is why for each module I provided our data, which should be available for you, for everybody, from your contact site or whatever. So I just remind you that we're trying to predict. Success of the grant, depending on the many characteristics. And success of the grant, so the initial, it's a cargo competition initially, just remind you. So this is a cargo competition that University of Melbourne submitted for data scientists for the reason that half of the money the university grant to the research results in unsuccessful grants. So that raises a question. So they 50% or even the ratio went down to 47% in the year 2008. And this obviously raised the question how the grant, the selection of the seed is wrong. And at least, so the normal university will expect at least that 70% of the invested money would lead to the successful research, and here the case that the success of the grant went down. That is why they submitted it to the machine learning to define the characteristics that, and to be able, first characteristics, secondly to be able to predict the factors that would influence the successful completion of the grant. So we have 4 types of sets. One is just training and testing. And the data was pre-processed, and how it was pre-processed from the original data, you can learn by looking at the Create Grant Data Ask Screen, which is available in the Applied Predictive Modeling package. And I didn't ask you to run, I provided you, I did run it myself, it works. So it takes an hour maybe to run. Though the training set contains around 2,000 predictors, to be exact 1,882, and that much for objects, 8,000 cases, we would say 8,000 submissions. And testing set is, it's not, as you can see, it's not an 80 to 20% division, as we usually did in the training and test set. And there is also reduced sets, just to see if, and because they played a lot with the data, sometimes they saw you don't really need that much predictors, like 2,000. Even the model with reduced number of predictors, like 252, is able to build a model with sufficient efficient power. Okay, so just again the reminder. So how we ended up with that much of the columns, like 1,182, and originally there were 15 columns. Originally there were 15 columns data for each individuals, and because there could be as much as 14 individuals in each grant, it's up to 14, but some grants contain less, sometimes contains more. So 210 was only the data about each individual predictors. And then there was an expansion from number of 252 to even 1,000 predictors. If you look at them on the table, you will see that many of them are just binary predictors. So you will maybe just let us have a look. So first load the data, and I would like you to look at the table of any of training, test, maybe reduce set and full set. And I want you to look at the columns you are dealing with. What are the columns? At least let us waste 5 minutes. You have to load training and test data as we did on the last workshop. And loading this data, resulting, you will see tables. On the right, please click on the tables and exploit and tell me what kind of columns do you see, do you observe. So does everybody have this data? So just tell me, you can do a structure. So how many columns are binary columns in these tables? Who can answer this question? How many binary columns in this data? How many real number columns in this data? Are all binaries? Are we just playing with pure binary data? What are the names of the columns? There's not a single real number columns.
The first one.
What's the name of the non-binary column? Number of CI, it's chief investigator. Number of the chief investigators. Non-binary, what else? What is it? Huh? Is the CI from Australia. You see, they sometimes it's interesting. So they distinguish if it's because the university is US University of Melbourne. They see if the CI in Australia, maybe you know if the chief investigator is in Australia, that could explain that it's too far away. And cannot really govern or supervise the graph. What else? Remember that I mentioned last class that there is a relation with the day of the week the grant was submitted and the year the grant was submitted. Who found? Tell us, maybe, who found an interesting column? Tell everybody. What are the interesting and expected columns are in this data. What else? Number, well, it's not that. Okay, number of people, it means it's not binary. It's not binary, that's true.
Unsuccessful. Success, CI,
yeah, so number of previous unsuccessful grants and number of previous successful grants too. Okay. Did you find this date, day of the week? And how day of the week, by the way, is encoded? As binaries, as 7 binary columns, or it's just numbers from 1 to 7. And the month also is encoded. The month is encoded too. You can find this. It could be in the reduced set, 252. There are nice functions like structure, STI, that would print you short and short summary. The short summary is a distribution. A short summary, if you provide a short summary for the data frame, it will provide you short summary for each of the column. Who is binary? Months. So it's, you just have 12 columns for the months, right? And they're binary. And for the days of week. And for the days of week. You see, so there are 2 options for you. When you will be modeling this kind of data, there are 2 options. You can make 1 column and encode it as a number, say month from 1 to 12. Or you can make binary columns and put in zeros, so say month of January. Everything is 0 except for the month of January and etc. So here is, that's why we have that number of predictors, like almost 2,000.
It's one shot encoding. One shot encoding. One shot encoding.
Well, it was practically shown that sometimes this binary encoding works better than maybe for short correction too. I'm not sure, but this is the practice. So this is, I just wanted to show you the practice of encoding. So we have 12 months and 7 days, 19 binary variables that would describe just the week. So what else? Did everybody load the data by that time? Who didn't? Who didn't load the data? Everybody did. Okay, let's then continue. I hope you have this block of, okay, we don't do parallelization. I hope you have this block of analysis from the last class that we did all to the rock and anchor. Meanwhile, let me write down the number for the previous class on the table so that I will continue doing it. Where is the pointer? This pointer is here. And the first model, why doesn't clean the desk? Okay, so who can repeat numbers for me from the last? So first will be AUK, then accuracy, then precision, then recall. Or let's call it not precision. Let's call it sensitivity, specificity. Better. The same sensitivity, specificity. Okay, first model we tried was linear LDA, linear discriminant analysis. Who can remind me accuracy on the LDA?
Not 9 to 1.
Not 9 to 1. It was accuracy. You. Okay, accuracy.
Not 8 49.
8 49. Okay. Sensitivity.
Not 8 25.
8 what?
25.
20.
5.
And specificity?
863.
863. Okay, then was after LTA. Logistic. First was logistic regression. Okay, logistic regression. LI was actually the first. AUK, logistic regression.
Not 908.
908. Accuracy.
Not 838.
838. Sensitivity.
Not 783.
Not 783.
Not 860.
860. Then what did we try next?
Yeah.
Okay, less. Okay. 0.
921.
921.
849.
Sensitivity.
841.
41.
854.
854. What else? That was it.
GLMN. What was the next? We haven't done it on the workshop, during the workshop, but I have the date.
Okay. What's the model? What did you say?
GLMN.
Generalized GLM. Okay, let's write it down.
Not 80, or not 80, not 931. Accuracy is not 857. Not 873. And not 848.
Okay. Now continue. That was all linear models. Now we continue with non-linear models. This is a control, train control function. We usually, when we would like to predict probability, there is a parameter for predicting probability. I haven't sent it out, right? Maybe I should. Okay, but then what we do actually, because you cannot run this model, so I always show how much does it take on my laptop with parallelization on 3 cores. But you can load, I will show you now a little bit slides about this analysis, but please load it as a data, MDA. It should be called like MDA something, MDA feed probably from the, so we're running it, you see, we're running it on a reduced set, meaning we're running it on a reduced set of 252 predictors. I think all the models I did on only 252 predictors, and this is just, so in general, if you would like to explore it in details, you run models both on reduced set, on the full set, and then you compare the performance. Please load our data, and then please do all this block of analysis that we did last class. This is how you see the model performance metrics, and I'll show you, this is the definer for the model was subclasses, but I have to show you the theory for you a little bit to understand what we've been doing. So, just, we had linear discriminant analysis. Linear discriminant analysis in the last class. So last class was linear discriminant analysis that creates linear boundary. And this linear boundary, to do this, it has some assumptions about the distribution of the predicted data, that it follows the normal distributions, that means of the predictors are different, and I showed you, so you have distribution and it should be different, and variance structure is independent from the data. The same as, so this linear discriminant analysis can be approximated to quadratic, to regularized, to mixed discriminant analysis. And so the boundary is already non-linear. And here is the idea that each predictor, remember, so in linear discriminant analysis, we approximated the data by the normal distribution. Here is the normal distribution, here is the normal distribution, then we said that the means are different, and then we plot the boundary and calculated probabilities given the normal distribution. Here is, we have not just one, but though again normal distribution, but there are multiple normal distributions. This is the trick with this modeling, with this model, what you are now doing. So that's why it does take a little bit longer to calculate. And actually, the number of distribution is a tuning parameter. If you look at my workshop, I will come back soon, later. Here is, if you plot, actually, did you load the model? If you plot the model, you will get this plot. And even when if you type the model, did you manage to load? Did you manage to load this MMDA fit model? Mm-hmm. No, I don't have it. I don't have it. No, but okay, you don't have the workshop, but you have the data, the grant data, MMDA fit data art. Did you load it? You know, I don't. No, you just, no, you don't describe, you just load. Without describing or saying object, you just load. And it should appear automatically. You just load the data, and then you do, okay. You just load, you don't ascribe the load to the table, you just load the data, and then you have the object MMDA fit. That you can approach and explore what the model was done. Did you manage? No? data. Dot R data. That I distributed, yes. Yes. No, you don't distribute, you just, because as if you had 1 hour and a half class, you have now, as you do it, as you do in the class, now you just float and repeat. You just float. Oh, what's the float? And explore. As if you here, I will, as if you plot, as if you run the model yourself, and then you have the tuning code. So actually, for this particular data, the best tuning parameter is just one distribution. So the model tried 2, 3, 4, 5, up to 8 to approximate. Though I wonder how does it work if you're, that's why I asked you to look at the data. And the data are binary. The most of the data are binary. How this binary values can be, binary predictors can be approximated by normal distribution, that's, you have to take into mind. So it's not really model. Though the parameter is, okay, though the parameters are somehow calculated. So probably we'll see what's the matrix. We'll see what the matrix in a moment. Okay. So what you need to do is what you need to do, MDA. So if you just type, when you load MDA, R data, and you type it, you see the results of the model training. And the final value for the model was plus 1. So we see it on the tuning plot, and also we can see it in the table and what is reported. And we can see this is the best value. Now, you do the predict. If you remember, you run predict. Maybe somebody can share this block that we created for those who didn't attend Can you share it in the group, please? So people can catch us more quickly. Are you already? Yeah, you send it. So the block is, so they sent, Mikhail, and those who didn't attend, they sent this block. So the block means, okay, the block means you predict you run predict twice, because first time you predict only classes without calculating probabilities. And the second, you predict probabilities. To predict probabilities, you have to type explicitly, type probability. And then you have both. You have the first object, the predicted probability object, contains data frame with 2 columns. And one column is successful probability of being successful, the second column probability of being unsuccessful, and you can notice that they just sum up to 1. So it's a redundant information, but still we do have it. It's a redundant information. So, and then, once you have this predicted probability and predicted classes, you can run confusion matrix. Confusion matrix requires only classes. So you have data from predicted class and reference from, it's actually, you just copy your block as we did in regression and replace and replace models and classes. And this is the confusion matrix, and then for ROC-AU, you have to load library PROC, and then ROC curve requires probability, because ROC curves is built according, so we put, as you remember the movie, we put different thresholds by probabilities. We're moving the different thresholds from 0 to 1 and calculate parameters of sensitivity and specificity, 1 minus specificity, which results in the ROC. That is why we need probability here. And these probabilities of being successful in the second argument, which is predictor, and the first argument and the third argument is just our class from our test set. That we observe, that we know what it is. To compare false positives and false negatives. You just copy all this block from analysis from the previous class, replace carefully models, don't confuse with the other type of models, and tell me finally the numbers, the metrics. Tell me finally the numbers and the metrics. And actually, this is what I would like you to do. If actually you do not look at the slides, please do it yourself. Just to train you that you understand what you are doing. It's the same block for analysis of every model. The same, okay, you don't have numbers, right?
The same as LDA.
The same as LDA. Well, because it's actually explainable, right? Because it's the best Bayesian parameter when you have one distribution, and LDA is just one distribution. So that's why it is the same, right? Exactly the same. I can just record them. Okay, 0, 8, 9, 0, 8, 5, 0, 8, 6, 3. It's just previous analysis, and this is actually, well, it does work somehow, though I don't know how they approximate binary columns by normal distributions. So did you get this? The same numbers? Yeah, they're not. Are they the same? Same? Okay, I can. If you have a question, please ask. Okay, so. testing class. Which you already downloaded. Would you allow this class probabilities? Did you predict probability? Oh, but yeah, well, you don't run that space around online 3.34, so you just close the object. It's not here. It's by default allowed to do this. So this is a good question. One question. One tool, and three. So, did it work? Did it work? Okay, let me see, let me show you the next slide. Okay, let me send around the slides though for you to help. Alright, I will send around the slides for the class, for this workshop. And you can continue with the neural network, but you also have, for those who already completed the MDA, can continue. There is an object data, our data neural network. So you do the same analysis. All these feeds on neural network, you can recognize them by names. These are all trained models. You just load it and then you explore what is the model, then you run predict and rock curves. Rock out curves in confusion matrix. You do all the block of analysis. That's why I always talking for the blocks. You just understand it once and then you just copy, replace.
Yeah.
Okay, I sent around the slides for today's workshop. Predict class, predict probability, then you create confusion matrix and you do outcrop curves. Okay, here we are. What are the numbers I have here? Actually the same, yeah, because it's my model, you must have the same. So, who didn't succeed? Tell me with MMDA. Yes, I can help. You did it. Okay, fine. You did it. Two, right? Yeah, and confusion matrix. Okay, fine. Then move to the neural network. We're finished. Huh? But didn't work. Let me see what's the error.
No errors.
No, that's in the code. Right? You cannot load it or what? Okay, MDA. Did you load MDA? Did you load from the data? Yes, there's okay. Then let's see where is MDA. Okay, you do it. Okay, so you need to run predict, right? Did you? But you have to describe it. Predict what? You do it, predict twice. No, we do. Okay, we predict on test set. Right? Do you have this block? No, but block, I mean, train, predict, confusion matrix, block. Where is the block? Here, just copy. Just copy. That's what I meant by block. Just copy, after you have the model. But probably just rename it LR was for logistic regression. Replaces MDA, then the model would be MDA feed, as we did. And this is all the same, okay. This is class. The same as probability in MDA and model, first the model MDA feed. And then you just reduce this class. This remains untouched because this replaces MDA and constructor A. This is probability from MDA probability. And the rest is staying the same. Now try to repeat. Starting from predict. This is enough. Okay, let's see if it works. You need library. Library key roll. Okay. Should I do it one by one? Let's see first. No. No, I think the object. Not just package. Okay. No, let's see. From MDA. This is from the model. This is wrong. This confusion matrix is wrong. We do it not from the testing. Confusion matrix is from the from what we predicted, and this is the took one class from the model. This is wrong. You see? So data is what the classes you just predicted. And this is your MMDA classes. That's MMDA classes. This is the list of classes you've just predicted. This is the first half. And this is you took train set from the model. That's right. So this shows you how you train classes without dollars. So just classes. And reference, look at this, is a testing class. Because we predicted the testing. This is your reference. Actually, this one is pretty. You have to divide string and this one. No, it's doing this line. You don't need this line. Here you have it. You just delete the whole line. Okay, then one is using that. And now it's more of this. It's just one thing out of the okay. Everything works? Okay, you continue over here. Okay. Yeah, for those who finish this MMDA, just continue with neural networks. Can be done in the same way. And I will just show you what are the neural network data is for classification. So tuning was too large. So actually, the neural network was tested size 1 to 10. This is we have a one layer. What we use here in the class is just one layer of neurons, but neurons could change from 1 to 10. This is decay parameter or learning rate, in other words. And I guess I even did not run it myself on the whole set of tuning parameter. I just looked up what was the best parameters. And the best parameters appears to be the 8 neurons with decaying 2. And this is how the model looked like. This is a train. This is a train. How I run the train, just with one parameter. Just with one parameter, it still took 1 hour 40 minutes. And we did centering, scaling, special sign transformation. Who remembers what is this for, the special sign transformation? Who does remember what we do with the special signs? No clue? We put outliers on the circle, so we kind of gather in outliers for special sign transformation. The maximum iteration 500, so this is not really a nicely trained network, but still what it does, because I run this just with 1 trillion parameters, I have this parameter. This is what 252 predictors, 8,000 samples, still, just for the sake of the exercises, I would like you to repeat, train our analysis. How's it going? This one? So this is for MD. This is for MD. And okay, tell me numbers for the neural network completed. Did you catch up? You haven't finished learning by itself. So this is what books? No, you shouldn't. No, you just load it. You load data. You load data, and so I have the data. I already have the trained model from. It's the name is something similar to NNFit or something. And then fit? What is it? That was
And the net feed
and the net.
dot our data.
This is for the neural network already? But did you manage to the MDA? You already advanced. Okay. Did you catch up? Did you think?
Yes, I uploaded it. Yes, I uploaded it.
No, but with this block of how we do classification, with this sense of confusion, occurs, words,
Yes.
no, this is the wrong one. No. Okay, this is them. These are classes for train model, and we predict. So what do I mean by model? Train, then predict classes, then predict probabilities, and then do compute metrics. So we don't have. When I asked them, can you copy from the last class, or you can do it? Actually, you can copy. You can create this block that you can copy from each. So you have this, but you predict on test, right? No, this one, the current one. In general, so you have, can you show me your MBA? So you don't do it, yeah. Use testing and use predict probabilities, yes. Yes. Okay, so neural network, then who finished neural can go in advance and run SVM. So tell me neural network numbers, please.
0.9193.
913, then
919.
919, okay.
842.
842,
820.
820,
And 852.
854. It's neural network. Then what I have is here, the same for support vector machine. The next would be interesting. So my 500 iteration for the neural network was 0.919. That's true. But in the book they run 2,000 iterations. And 2,000 iteration led to slightly decreased our value. That's what they thought. Okay. The next support vector machine.
This decreased down, is it because of overfitting?
Could be. We don't know. Overfitting, we have to see the tuning plot to see if there is overfitting. And with neural network, it's not reasonable to do it in class. We have to train. So let's see support vector machine. Support vector machine. So the same, there is a data that you can load and have the model already trained. And let us just see what was the parameters. The parameters for the support vector machine was, what did I run with? So I did not run the full grid. The full grid was different value of cost parameters. 9, these are power of 2, so starting from -4 to 4, there are 9 tuning parameters, and I just looked up that the best tuning parameters C1, and then that's why I just run this model. Sometimes there is a comment that it did not work for me with 2. And do I have the? It's still time consuming, even on reduced set, even on 3 parallel cores. It took 1 hour 30 minutes. So you see, it's my laptop. My laptop is already 7.5 years old. To be exact. So it's not really a fast machine, but still doing. Can do some calculations. Support vector machine. So that's SVM radial, SVM. You see, it's actually the same as you run with regression or with other, and this is the most popular kernel of SVM. And here we have the results, how the model performed. Again, you see I just didn't run all tuning parameters. And the same you can do predict, world curve, and have this I can write it down once myself because you have the same model, 0.293. It's our curve. Okay, we're almost done. And you tell me sensitivity, specificity, and accuracy for SVM. Can you tell me?
0.8 CU. 0.851.
8.1. Sensitivity. Sorry. Now this up to you. No, this so this was okay. I just moved it. I shifted it. 0.851, and this is 0.820. In accuracy, no. In accuracy is 0.840. Okay. These are a number for SVM, and the last probably model, I'm not sure if it's last or not, Canary's neighbor, still takes 1 hour, 10 minutes, or 3 cores for me. I also did not run the full grid. I just looked up. They actually, in the book, they have the Turing grid that's try nearest neighbor, different values from ending up to 451. As I remember, the model performance is always grew up while adding these neighbors, 451. Even if, I don't know, if you continue, you probably will go up to, I probably have this in the book, because they just end up with the 451 nearest neighbors. Probably 500 will be even more, I do not know, and they, for some reason, they're probably also tied to iterate through different, this is naive bias. No, it's not the last one. Naive bias is not a nice model, we have to run it, but we can neither, there is a special set, yes. Okay, for those who done with KNN, KNN is not really good before here, we probably even want to run it. For naive bias, there is a special data set that I also redistributed. And I'll tell you why. The variable should be processed. We cannot use it just because of the reason of too many binary variables. And we did convert them to factors, and I'll show you. So, to factors meaning you come back, and that's you do the numbers. So you do not do 12 columns for the months of the year. You do one column, and number is 1, 2, 3, 4, up to 12. Also, the number of chief investigator in department takes one of the 4 values between 0 and 3, has very right skew distribution. That's why some transformation required for the data, and you can do it yourself with the package from Create Grant Data, but we don't do it. Instead, you have this. You have this 3 sets of naive bias data: NB predictors, NB testing, and NB training. Am I too fast, or you? Did everybody finish with all this model, neural network, SVM? We can skip Kainan. So we can skip Kainan, so you try everything. So I think it's just copy and paste, right? It's not really, because you don't train it yourself, it's not maybe that interested, I will not tuning parameters with me. So we can, before you can load this data, meanwhile I would like you to show some theory for naive bias to show you what it's all about. So here is MMDA. This is a neural network. Just to remind you, what is the neural network? Where is the nonlinear relationship, and where it's actually a classification task. In regression task, we model the relation between predicted and hidden neuron by sigmoid, but then it was a linear combination of the new predictors. The difference between classification tests, that the output is also modeled by sigmoid function, meaning we scale variables and put them to the values that easily to manipulate and ascribe probabilities. That's how the probabilities are obtained in the neural network. It's actually sigmoid function produced with probability of the output. And in regression, because we predict here we predict classes with probability of class being a class 1, class 2, and class C. In general case, there could be many classes, and in regression, the output is a linear combination of hidden units. Then this is a slide from the books when they show 2 tuning parameters, weight decay, number of models, and how the classification curves actually uploaded depending on they have just randomly 2 predictors, though they didn't say which one predicted. No, it's actually not discussed. It's the play with the data we learned our It's not a grand data. It's a data from the workshop when we learned classification metrics, when we have this plots that should be separated. Or even even not there. It's from the first workshop, from the third workshop, when we learned how we can resample data, and let that play to this data, and show how the curve, because it's non-linear classification task, the classification boundary is no more a linear curve. And with neural network, the curve could be that peculiar shape, as we see on the slide. Neural network for the ground data. From the ground data, that's already we mentioned that the best model was the 8-hidden user with the lambda wave decay and learning rates 2. And what are the average network models? Sometimes you run, this is like ensemble. An ensemble can be also done for the neural network. If you run different, say, 10 networks to do the data, and the results are average, then the best model, and this was the slide to show what here is. You see modules 1, modules 5, modules 10. So you run, say, 5 different modules, and then you average results. Or you run 10 different modules, and then you average results. And when we do this, and they did it with the ground data, for example, you can see here that the best model was a 10 networks, and then 6 hidden units with the learning rate of 2, though the ROC curve is not considerably high for this task of ground data. Neural network is not the best performer. Because maybe we didn't train it much, it's not enough layers, etc. This is a special sign transformation. This shows you how the special sign transformation could affect the result of the model. So these are 2 tuning plots. This is no transformation has been done, and this is single model. This is model neural network model averaging. And this is showing us how model averaging actually improves the model. And this is raw Haroop characteristic. This is special sign transformation. And this is, again, model averaging. Model averaging. And this is 0. So you see the best performance was for the blue curve. The blue curve corresponds to the wave decay of 0.1. And it reaches a root value more than 90%. You can see it from the plot. Though, without transformation, this blue learning curve, you see it's below 90%. So this is the effect of special. So sometimes it does help, and actually it doesn't have any. With learning rate of 2, special sign and transformation have the poorer performance than on the upper side. This is what does it show. So the result of the graph is just yes. The result of this graph, yes, special sign transformation does improve the model, and the model performance, yes, it does in general, but mostly for the model and model averaging specifically. Yeah, here's kind of contradictory, it's not, yes, so it's not. So actually different learning, different wave decays or learning rates affect the result of the model transformations. Here is support vector machines, just to remind you, actually support vector, we use it for regression, but initially it was invented specifically to do classification tasks. And support vectors, so you define somehow the boundary, and support vectors are, this boundary is epsilon, and support vectors are those dots, are those points that lie on this boundary. We do not take all the data into the modeling. We take only subset of data that are close to the boundary, that are difficult to discriminate. That's the idea of support vectors. So because these points are obviously easily to classify, they are far from them by itself. So this data just excluded from analysis, and the whole analysis is done on the so-called support vectors. And the success was specifically for classification tasks. We show how it's again the combination of linear transformation, and let's see tuning parameters that we did not do. So we run it just with one tuning parameter, and here, if we were able to run it, we would see this kind of tuning curve. So this is for the full set, and this is for the reduced set. So full set is 1,800 predictors, reduced set 252 predictors. And you see that reduced set actually achieve better performance even than using the whole set of predictor. This is the cost parameters, some cost parameters that achieve, and this is the tuning plot for the support vector machine radial kernel. Canaries, that's what I told you. So they just have this tuning plot which iterates through the neighbors successfully up to this value. But you see on the graph, the curve is always growing. So probably if you continue further, you would achieve even better result. But in general, results are not really successful. Though, KNN, I was recently, there was a colloquium, you can look up it on the Department of Computer Science website. There's a colloquium. There was a guy from Yandex, which actually, I thought KNN, was never used. But he praised KNN and showed that in many applications, which requires time, fast processing, and some results, KNN is widely used and shows many examples. So do not discard KNN at all. And you can watch out. The colloquium was, I guess, 1 month ago or something. So KNN is not really a bad model. Sometimes it does help, specifically if you require time. You need to save time, and Yandex need to save time and more interactive tasks. But here you see it's a poor performance. So of all our OPS of 92+%, the 80% is just really, even uncomparable. So naive bias, actually, I think the last module, maybe I just, what, do we do break, or I continue and we do break after that? Or we do break now, and then continue with naive bias, and I break now? Okay.